Okay. So last time we were just getting into Newton's laws. The first law so today we'll talk about second and third law. Yeah. The first law, not going to write out the full statement again, but we said that the purpose of the first law was defining an inertial frame. Yes. Oh, yes. Okay. So then one thing to find an inertial frame of reference. The rest of Newton's laws apply, and also the test involved in the first law was, if there's zero force, then an object should behave in a certain way. So how does the object behave if there's a non-zero force? Well, the second law tells us in an inertial reference frame, or an object momentum that equals. Okay. Again, there are many ways to write the second law. This is just one way of framing it. But it basically says the net force acting on a system or on an object is equal to the rate of change of momentum of that object. Very naturally asked, what's momentum? So momentum, P, is equal to the mass of the object times its velocity. But can we say anything further? Well, if we're dealing with a system where the mass of the object is constant, we can go further. So if m is constant, then what can we say? We can say F net is rate of change of momentum. Momentum is a vector. I can plug in the definition of momentum and B. And if the mass is constant, I can pull the mass out. And so we get mass times dV dt. And what is dV dt? Acceleration. And so this is how we get the more familiar form, which you've probably heard before, of F equals ma. But there are two caveats to that. One is it's not F equals MA, it's F net equals MA, right? And the second is that this only holds if the mass is constant. What's an example of a system where the mass is not constant? Yes, Jada.
An oil truck going down ramp and it's like leaking oil.
Yes, something that's leaking oil as mass is changing. Any other examples? Yes, Glenn.
A rocket going up in the
A rocket going up in space, yeah, is the exhaust. Yep.
Like a snowball rolling down a hill.
Snowball rolling down a hill, gathering more snow. Yes. Yeah, sure. Black hole accreting, ingesting more mass. So these are all examples of systems where the mass is changing, either decreasing or increasing. And in those cases, we can't use F net equals MA. You'd want to go back to the original dPdt. This is still true in that case. And you can apply it, but then you have to account for the rate of change of mass as well. All right. So let's do a few questions. Go ahead, get your voting papers out. Last time we talked about that. Let's try this one. Right. Get ready to vote. Show me your votes. Go ahead and discuss.
I said
That makes a lot of sense.
If it was just graphic, it says metaphor. So we
I could also get
but I think there's also that works.
No, we know there's a
Yeah.
I didn't even, I wasn't even planning on taking a class ever in general.
Say you're.
Yeah, yeah, so just saying, being, oh my god, that's not gonna be fun. But if it, that isn't just, like I said, it was 5 questions.
Okay, all right.
Again, and that's.
All right, get ready
How is it insufficient?
and show me your votes. Okay, A is correct, yes. We don't have enough information. We know what direction the velocity is in, right? It's heading east and upward. But we don't know if that velocity is increasing or decreasing. Or constant even. So we just can't say anything about the acceleration. And if we don't know the acceleration, we can't say anything about the net force. So the important concept here is don't confuse velocity with acceleration, right? At any given moment, the velocity and acceleration can point in totally different directions, right? If you know how the velocity is changing with time, then you can say something about acceleration. But if you've just given a snapshot at a single moment, the velocity at that moment has nothing to do, it's totally independent of the acceleration at that moment. So one does not tell you the other. Okay. What about, yeah. Question? Sometimes the clarification is needed.
Does air resistance exist?
Does air resistance exist? Not relevant, I would say. As in, it could not, you already have the information you need. And show me what you did. I can discuss. So to clarify, in case 4, the object we're looking at is the box, not the truck, just the box. That's Okay, sounds like that clarification changed some minds. Go ahead and okay. Mostly for F, some for E. F is correct. Focusing on the box. So yeah, we'll go through them. So cases 1 and 2, we agreed that the speed that the velocity, both speed and direction are constant of the object, and so there's no acceleration. Yep, okay, so there's no acceleration, so there's no net external force. 3, the speed is constant, but it still has what kind of acceleration? Centripetal acceleration, because it's going in a circle, so the direction of the velocity is changing, so there is acceleration, so there is an external force. And then here the box, because it's a frictionless surface, the idea is the truck would accelerate forward, the box would just stay where it is. And yeah, and then like once the truck is completely out from underneath it, then it will like fall down. But we're looking at the moment when it's still on the flatbed, the truck is just accelerating. Questions? Okay. Oh, yeah, question, yes.
In four, wouldn't you have to specify that we're talking, like that the inertial reference frame is?
Oh, I mean,
Is the truck?
well, no, the truck is not an inertial reference frame. We're viewing from the side of the road. Well, I mean, the assumption here is that unless specified, you're viewing from an inertial reference frame, unless otherwise specified. The truck would not be inertial because it is accelerating with respect to the ground. And so we're treating the ground as an inertial reference frame.
And what exactly is happening?
So in 4, it's sort of like, imagine this is the bed of the truck and this is the box. And so then the truck suddenly accelerates and like the box is, yeah. And so then if you waited long enough, it would just come off and then just fall down. But yeah. Oh, yes.
Is the box like accelerating backward, or like is it just like gonna be at first?
Good question. So from the viewpoint of someone on the ground, the box is staying where it is. The truck is what is moving out from underneath it. From the truck's point of view, the truck is not moving and it's the box that's accelerating backward. But the truck is not an inertial reference frame, right? So you have to like be cautious with the statements you would make in the truck's reference frame. Yes.
So when an object moves in a circle, like even though it's got constant speed, it still is accelerating because it's changing direction in both ways. Is there a version of like Euclidean geometry where the circle is a line?
I was like, there's no way they're gonna ask that. Like, I was like, oh man, you did go there. Okay. Yes, if your universe was a circle, then you could. But that is not something we're going to talk about in this course.
That's so cool.
All right, other questions? No, okay. What?
What is that?
Well,
No,
it'll take too long. It'll take too long. All right. Okay, all right, yes, the fan on the card. Well, actually, all right, before we do the fan on the card, I didn't get around to this last time. Let me try and do it this time. Let's see if I break something. Yeah, so, oh, yes, no. Do it from this side, okay.
Oh, you can't see.
So. Oh, on the camera, yes, oh, thank you. Let's see. Okay, so what is going on over here? This is sort of a mix of say first law, second law. There is a force, right? There is going to be some friction between the tablecloth and the objects on top, but it's very little force, right? And if I do this quickly enough, it'll be exerted for small enough time that the momentum of the objects wouldn't change very much. The natural tendency we know in the absence of force is if they're at rest, they stay at rest. Okay, so hopefully that's what we'll achieve. If not, probably should do this at the end so I can clean up easy. But, okay. Oh, All right, so. Okay, and let's talk about then another demo. That's a test, yeah. All right, so we have a cart mounted on a track. The track is low friction. And the cart has a fan on it. So when I turn the fan on, assuming it's a fan that blows, right, not sucks, then what will the cart do? Versus. No, you just need to know that it's going to blow air away from the fan. Yeah. All right. So what do you think? Okay. Most people say it will move to the left. Let's check. Yep, move to the left. All right. So what's going on over here? Anyone want to take a stab at explaining it in words? Yeah.
Because like the fan, when it blows out, it also like sucks air in from the other way.
Okay.
So like it like wants to like take the air from.
Ah.
Right.
Okay. We could look at it that way, but from a force point of view, we're going to look at it slightly differently. Yanni, yeah.
I'm thinking about Newton's third law.
Ah.
Chain reaction. So when the fan pushes air out, the air pushes the coil in with the same magnitude of force.
Yes.
When the cart moves forward.
Yanni is exactly right. So this actually brings us to the third law. Let me just put up the screen briefly. So Newton's third law. In equation form, this is quite simple. Says if you have two objects interacting, A and B, then if A exerts a force on B, then B will exert a force on A, which will be the same magnitude but opposite in direction. That's the minus. Colloquially, it's called for every action, there's an equal and opposite reaction. Which, yes, is true, but it sometimes misleads people. They think that one happens before the other. No, these are simultaneous events when immediately as soon as one starts pushing, the other one pushes back. So here, what we had was the fan, force of the fan on the air was that way. And so there would be a force of the air on the fan, which would go that way. And so because the fan was attached to the cart, the whole cart fan system felt a force, which moved it to the left. Questions about this? Okay. What if I just put the screen up and I realize I need to put it down again. What if I okay. Supposing I have a book on a table. You don't need more time? Need more time? All right. Ready? Tell me what you think. Okay. We have, yes, there's only two choices, A and B, and there's a split. Go ahead and discuss.
It's
The reaction force is
I think it's B because
related to the
it should be like
reaction force
to
the book, so different objects, but because like
So I mean, you're correct, like Addison's argument is like the more so that's
They're not.
The force on talking about.
we apply to different objects.
Yeah, so the force of gravity is the force of the earth on the because of the reaction to that would be. Always has to be two objects that are each other or like affect each other.
Are they actually the same type of
So like force that the book exerts on is also the force of gravity. The force that the book exerts on the table is also gravity.
Someone asked you that?
Although it's not the same two, you can look at an equal sign.
well, I guess
You don't know about the. Those forces. But
There is an action reaction. Okay. All right, let's see what people think. Okay, mostly for B. B is correct. It is true that these forces are equal in magnitude and opposite direction, but that is not enough to make them an action-reaction pair. An action-reaction pair always has to be of the form F of A on B and F of B on A. So if the force is the force by the table on the book, then the reaction to that would be force of the book on the table. Okay. And if the force is force on the book due to the earth, then the reaction to that would be force on the earth due to the book. Also, action-reaction pairs have to be the same type of force. So the force on the book due to the table is a normal force. And so the force of on the table due to the book will also be a normal force. Okay. And similarly, the force on the book due to the earth is the force of gravity. And so the book is also exerting a force of gravity on the earth. Okay. Yeah. And it's exerting, in fact, it's exerting the same amount of force. As strongly as the earth is pulling on the book is pulling on the earth. Why do we not notice that? Oh, yeah, go ahead.
The Earth's mass.
Yeah, the Earth's mass. The Earth is too big. Yes. Yeah, the Earth has like, what was it 10 to the 24 kilograms, something on that order? Yeah. So the Earth is so massive that we don't notice its acceleration, right? And if the force might be the same, the accelerations are very different. And so we don't notice any acceleration of the Earth due to the book, but the acceleration of the book due to the Earth, yes, we can see that very easily. Okay, so what we have here is an example of a free body diagram. Okay, and we'll be using these a lot. So free body diagram, what we do is we basically reduce the object to just a dot, and then we show all the forces acting on that object. So notice that I haven't depicted the force of the book on the table. Oh, sorry, yes. Oh, the camera, yes. Yeah, okay. Notice that I haven't depicted the force due to the book on the table, because that would belong in the table's free body diagram, right? Not the book's free body diagram. So in the free body diagram of the book, I only focus on the forces acting on the book. Don't care what the book does to anyone else. Okay, so free body diagram. Maybe just abbreviate it to FPD. So let's try some questions related to that. Come back to the fan in a bit. Yeah, let's start with this question.
What's the other direction, or is it specifically?
It's specifically as given in the diagram here.
But it just said, but depends on the magnitude, but not the direction.
So see it?
It just needs the magnitude of the, not the direction to change for T.
Oh, I see. Okay. Well, I mean, we've been in the diagram, we've been specified what the direction and the behavior of D is. So yeah, D is just talking about magnitude. Yeah. All right. Show me what you think. Okay. All right. Mostly for C, C is correct. So the idea here is that we're ignoring air resistance. So that's not an issue. So in that case, what are the forces acting on the elevator? Force of gravity, force of tension. All right. And the velocity is upward and constant. So what does that tell us about the acceleration? Zero. Acceleration is zero. So I'll just put a note here on the side, acceleration is zero. And so then that tells me that the net force must be zero. Okay. So if I apply Newton's second law here, what would I do? I would say, okay, F net equals ma. I'm applying this in the y direction. Let me say that up is positive y. So I'd say, okay, F net y equals MAY. And so then that would be FT minus FG equals 0. Okay. So when I was looking at the net force in the y direction, Ft is entirely in the positive y direction, so I have plus Ft. Ft is entirely in the negative direction, so I have minus Fg. Notice that these are magnitudes, these are not vectors. Okay, you have to be careful about distinguishing between magnitudes and vectors. Yeah, and so then Ft minus Fg, and then the acceleration is 0, so equals 0. So I can say that these two are equal. What about this case? Now we are looking at the person in the elevator. One more back. Good one back. All right, show me what you think. Okay. All right, mostly for A,
I was thinking because the elevator is going down, it's slowing down, the acceleration must be upwards
Yes.
in the positive y direction. And because of that, net force is also upwards,
Yes.
meaning that there has to be a greater normal force than force of gravity.
Yep, that's exactly right. As Najveer said, we're told that the velocity of the elevator and the person are downward, but we're also told that it's slowing down. So that tells us that the acceleration is upward, right? In the positive y direction. There. So if I draw an FPT of the person, the two forces acting on the person are force of gravity and the normal force. But the acceleration is upward, right? So the net force must be upward, and so that's why I'm drawing the normal force larger than the force of gravity, so that the net force will be upward. What would the equation I write for the person look like? Yeah, pretty more space there. So here, if I apply the second law, again, assuming up as positive y, so then I have f net y equals ma y. I would say fn minus fg equals ma. And then if I, for example, know the acceleration and the force of gravity, I can figure out the normal force. Yes.
If velocity is decreasing and the rate of change of velocity is negative, so
No, if velocity was just like a scalar quantity, you could maybe say that, all right? If it was just a magnitude. But because velocity is a vector, right? When we talk about the sign of the rate of change, right? When you talk about the sign of the acceleration, it's just telling you which direction the change is pointing. So initially it was a large downward velocity vector, but then as time passes, it becomes a smaller downward velocity vector. So what direction is the change in velocity?
then it would be positive.
Then it would be upward positive, yes. Does that?
No, because if it's slowing down, that means that at the beginning of its motion, the velocity is great,
Yes.
and then
Well, great speed, yes.
and then as you progress, speed lowers.
Yeah.
And so that rate of change is still negative, right?
Well, the rate of change of the speed is negative.
Correct.
But that's not what acceleration is.
I think
Okay.
Yeah.
add to this,
would it be different if it was slowing down, moving upward versus slowing down, moving downward?
Yes, I mean, the direction of acceleration would be different.
So. But this elevator is moving
Downward,
down and slowing down,
yes.
so the acceleration
Acceleration is
is up.
up.
If it was moving up and slowing down, the acceleration would be down.
So you want to break the idea of the sign of acceleration telling you something about the speed. The sign of acceleration simply tells you which way the acceleration is pointing.
Right, but I know the speed remains positive.
The speed remains positive. Yes, how's it? Yeah, sorry.
Also, if the second velocity has a smaller magnitude and it's still pointing downwards, a negative minus another negative is going to be positive, so then the acceleration would be in the positive j hat direction. If you're trying to do it, but it would be too much.
No.
I understand that. But maybe I.
Okay, after class. All right, we'll talk about after. Other questions? All right. Okay. Did that. All right. Yes. Quick one. I won't give you too much time. Show me your votes. Okay, all right. Some of you fell for the trap, some of you didn't. We don't know. You just know the direction of the force that tells you direction of the acceleration, nothing about the velocity at that moment, right? It tells you which way the velocity is going to change, but not the velocity at that moment. Okay, so yeah, let me do this. So I'm going to take you through this problem in the remaining 7 minutes. I'll sketch it here and then use the blackboard. So we have a block sitting on a ramp. It's tied to a rope, which is attached to a wall. And we are interested in the forces acting on the block. So that's the general situation. First, let me put this question to you and then we'll analyze it further. So which of these is a valid free-body diagram? You know, 3 choices, A, B, or C. And show me what you think. All right, everyone for B, B is correct. Though in fact, what I would normally do is I would use this diagram from B, but I would use the tilted axes from option A. But I'm going to show you that regardless of which set of axes you choose, the answers will be the same, but it's going to be much simpler if you use the tilted axes. But yeah, so let me at least show you one of the ways very quickly. All right, so the forces, we said there is the force of gravity, there is the force of tension. This is at some angle theta, and then there's the normal force. This is the right angle. And first, let me use these axes. or in fact, let me draw those axes right at the object so that you can see the angles more clearly. So this is my x-axis, and this is my y-axis. So then we can see that, oh, if this angle is theta, this angle would be 90 minus theta, and then this angle would be theta again. So I'll mark that this angle is theta. All right. So I have two directions, so I'm going to split up my F net equals MA into two directions, right? So I'll have in the x direction, F net x equals MAX. And so for F net x, I need to find the x component of each of these forces. So what is the x component of the force of tension? Yes. Ft cosine theta. Okay, x component of the force of gravity? No, x component, so just zero, okay. X component of the normal force. Yes, go ahead. Oh, I thought, just check it, oh yeah, check it, go ahead. Oh, or yeah, yeah. Fn sin theta, and it's in the negative x direction, so minus, so yes, we put minus Fn sin theta. And then equals 0, it's not accelerating. All right, so this is for the x direction. For the y direction, similar thing. Right, so call them out. What would it be for the force of tension? Yes.
Ft sin theta.
Yep, that's it. Ft sin theta for the tension.
Plus
Okay.
and cosine theta.
Yep.
Equals
Plus
to
Fn
Ft
cosine theta.
equals
and-
to F.
Well, yes, but we're putting all the forces on this side, right? So we would write it as minus Fg and then equals 0 because it's not accelerating. Questions about either of these? Okay. So assuming that we were given the mass, supposing we wanted to find the tension and the normal force, we have two unknowns and we have two equations, so we should be able to solve this, assuming we're given the mass and the angle. So I would need to isolate one in terms of the other. So I could solve this for Ft. I can say Ft is Fn sin theta over cosine theta. And then plug that in over here. And so then I would get, plugging in for Ft, I would have Fn sin theta over cosine theta times sin theta. And then plus Fn cosine theta and minus Fg equals 0. Both of these are Fn, so I could combine them. I could put them on a common denominator. And so then I would have Fn, I'd have sine squared theta plus cosine squared theta all over cosine theta minus Fg equals 0. Right, I just combine these two terms, putting them on a common denominator. But sine squared plus cosine squared? 1, right? So the numerator here would turn into 1 times Fn. So I get Fn over cosine theta minus Fg equals 0. And so Fn equals Fg cosine theta. And Fg is just mg, so that's mg cosine theta for Fn. Once I have that, I can plug in over here, and I would get Ft equals mg sine theta. Yes. Oh, the angle, yes. Okay. Questions about any of these steps? Okay, we're past time, so next time I'll show you how it's much quicker if you use the tilted axis. But we'll stop there.
Never happened. I don't know.
And also was one
Oh, yeah. But.
I have stickers.
Yeah.
Oh, yeah.
I think, assuming your numbers are right.
I am transferring to right now.
Oh,
So,
okay.
and
I put a screenshot like this.
Yeah.
Yeah, I thought I was just gonna say, I realized that.
Oh.
Yeah, okay, sorry,
Okay.
That's. When this one.
Yesterday.
The homework is due on Monday night.
It's wrote X of.
Okay, I'll rate it this time, please get the timing correct, yeah. Yeah, but make sure to include the original submissions in there.
It's really cool, I already.
Separate correction, thank you. Yes.
When it's like. I'm sure I'll tell you what.
This thing kind of crazy. Launch open.
Yeah, that's not.
Thank you.
For when we'll just share.
Sorry,
Do you want me, like, when you're just. I'm not writing in vector form, it would like be using the 8.68i plus 3.0.
Yep.
Do you just want me to have that you write out like the problem, or can I just write the C?
Okay, this one. So normally I would say just the final answer, but one other thing for on the examiner is you need to show the formula that you're doing before you plug in numbers.
Well, I mean, Alex, that's about 5 minutes.
Yeah, the initial plus 80, right? So just show those steps.
Yeah.
It's
It's like,
he's like
a scratch.
Yeah, the guy wrestling.
And then I remember.
I think you showed me like
Yeah.
they showed me.
No,
like,
it's the-
oh,
Honestly, this one is fine. Yeah, I'll.
Yeah, I'm gonna ask him.
Give more.
I mean,
Oh
it's-
my god, it's huge. Like, that'd be about 6 months.
So you want me
I can't see that.
It's like actually terrible.
Is this?
Sometimes like he won't.
So give me two. And then.
He's like in the middle.
homework-
The middle of
You see this image on.
Not see everything. Like, what is this? It's crazy. That's terrible.
I was gonna.
We didn't know where to start. It's like.
What's the-
Whatever sensors.
Okay, so I was. Okay, alright, so. Yeah, just turn in
It's like really good, it's the same velocity, like everything. Like the incline is just like.
At my club, I was like
Like a
61.
negative. So,
Maybe staple them together, so because it's starting to get confusing. I can just-
Yeah.
Now I'm like shrimp.
I think we
If you don't stuck on my own, I'm messing up.
Thank you so much.
This is our.
You bet every time.
Yeah.
Any comments?
Not really, I'm reconsidering where I put this fan demo, but since it's here, I'll use it today,
Sure.
but yeah, in the future, I'll probably shift
Mind
it.
shifting to a different spot, yeah, no problem. Okay, go.
Let's see, second round on push for this.
Yes.
You want to set it?
Look, today is Wednesday.
But second, that is Thursday.
Yes, so tomorrow night.
I don't know whether.
No, so you first submit your homework on Monday night. Right. And then the idea is that if you submit it on Monday night, we'll be able to grade it and return it to you today. Okay, and then we bring corrections and you submit on Thursday.
I was shocked at breakfast.
Is that?
Oh, I see, so the second.
Bro, I really had it. 2 meetings, you're sitting right there. I was like, yeah, I'll do that, I'll do that. Hold on. It's so sticky.
The revision
Friday.
No, Thursday. The deadline is for you, not for me.
It's been a constant.
Yeah, so you submit the revisions on Thursday night.
Yeah.
Yes, but this time because you submitted the first one late, right? We haven't gotten a chance to grade it, so I'll grade your submission this time. But please make sure to do it on Monday, otherwise it doesn't give us enough time to return it to you.
Okay.
See.
Hey.
So I can make a copy, start complaining that I can make, I'll do it, make it.
Oh, I should. Yes, that'll be fine. Yeah, okay. Send me an email if you can. That's fine.
Okay, alright, thank you.
I'm gonna declare.
Okay. Okay. What is the next?
Can I ask you a favor?
Yeah.
Can you go to the lounge
I think that
and grab the blue
I
bag?
was kind of the last one. It really has my little bag, material, so that really. So I'm just gonna. Yeah. Yeah.
Makeup card.
Yeah, I think it's gonna be sometimes.
Okay, or I'm not picking that word.
No, this is like free. Like I take soils. That's all. It's my best. If you always go to sleep, it says like.
Yeah. Everything you feel trapped.